Thank you, Professor Kim, for that insightful and exciting talk and for walking us through the exciting world of semiconductors. So without further ado, we can get started with the Q&A session. So one of the question coming in from the audience was, could you please comment on ion transport and effective mass evolution over time in terms of simpler systems like electrolytic cells or energy devices?
Oh, could you repeat the question again one more time?
Sure.
Sorry.
Could you please comment on the ion transport and effective mass evolution over time for simpler systems like electrolytic cells or energy devices?
Oh, the effective mass you mentioned, right?
Yes,
Oh, effective mass for this oxide semiconductor?
right.
Yeah, I mean, there was little part that was there in one of my slides. Effective mass is like silicon. Effective mass of this the electron in the oxide semiconductor uh is lighter than the effective mass of hole. So that's the one of the reason the oxide semiconductor, N-type is more popular and performs good transistor performance. Okay, so and what's the second part of the question? The
Uh,
effective mass?
the ion transport, how does that vary over
Ion
time?
transport. Ion transport. Oh, this one, ion transport, the only thing that I can tell you is, see, in the oxide semiconductor itself is amorphous, solid phase, right? So you have to give thermal energy or optical light energy in order to excitate maybe some of the things in the forbidden gap to the conduction band, or still, even if the energy is not sufficient, still, even if you give some energy, the they cannot go escape from the forbidden gap. Okay.
Okay, thank you so much for the response.
Mm.
There is another question coming in regarding oxide semiconductor-based displays. How does the carrier mobility of oxide thin film transistor materials such as indium gallium zinc oxide influence the operating frequency or the refresh rate of the display?
Ah, that's a good question. Okay, so indium gallium zinc oxide, if you make the semiconductor material with this indium gallium zinc oxide, the off current is become very low. Transistor function is on and off. So you know the mean of on. When you put some voltage and it's on state and supposed to give a high current, right? That's on. When you put a certain voltage off state, it's supposed to give a minimum current. The zero current will be the super, but zero current is impossible, right? You cannot make that kind of transistor. So anyway, so every screen there you're looking at, you don't realize from top to bottom, they're giving the data 60 times per second. Okay? If they reduce to even 30 times, 40 times, you start to see the flickering of screen, right? So you don't want to see that kind of screen. So that's why people maintain the 50 hertz or 60 hertz. But if you use oxide semiconductor, the off state is very low current. So if you use oxide semiconductor, even if you give a 30 hertz, 30 hertz or 40 hertz, you don't see the flickering. So that's the beauty of oxide indium gallium. So not only indium gallium zinc oxide, many other semiconductor oxide semiconductor material does the same. So the summarize is the answer is the oxide semiconductor can give very low off current. If the off current is low, you don't have to give the data for the screen that often. Okay, that's the way you save the battery. And yes, I hope it answered your question. Okay.
Thank you, Professor Kim. A related question to that, how does this relationship between the carrier mobility and the operating frequency affect the power consumption and
Oh,
battery life?
yeah, that's a good question too. You know, the transistor in every pixel in display, the switching transistor is unbelievably long time off. Only very short time is on. So we are using that because most of the time the transistor is off and the capacitor is holding that voltage. That's why it has one transistor and one capacitor. So it's nothing to do with the high mobility. One more time is due to law of current. If it's law of current, you can play with this hertz, 1 hertz, 10 hertz. Okay. If the mobility carrier mobility and field difference is slightly different, but anyway, the mobility is good, high, then you could make transistors smaller. You know what happened? If you make it smaller, then you could have higher resolution, more number of pixels, right? That's the difference though. Okay.
All right. Uh, One of our attendees would also like to know your thoughts on the use of metal oxide devices, particularly the amorphous indium gallium zinc oxide or ITZO or ITGZO in the realm of electrical and optical biosensors. What are the scope of these metal oxide devices under the area of electrical and optical biosensors?
Scope. Oh, bio. Yeah, I mean, so now you understand this oxide semiconductor beauty. One example is I keep telling you this law of current, right? So it's good for display and memory. And another aspect is, they are making this transistor, oxide semiconductor transistor on glass substrate. Glass substrate is huge size. Conventional electronic, microelectronic device, people make on the wafer. Silicon wafer, 12 inches, like large family size pizza size, right? But if you use a glass substrate, what's the difference? You can make the device very cheap, low for minimum cost. That's the beauty. And so that's the one good example for photo, applications or bio applications is slightly complicated, but that's the one advantage. So you can make this device. And as I explained, you could even use solution process. No vacuum needed. If you use a solution process, you could choose the material, all different materials. So that's the thing. So yeah, that could be the advantages for other applications.
All right. Additionally, is there any doping technique that you would prefer to use for these metal oxides?
Yeah, doping technique, yes. Now, commercialized people do the Sputtering one is easy. When you make the target, the original target material, you just include that dopant material. That's the one way. Another way is, conventional IGZO is there, and you put the open target and you do the core sputtering. And this is the easy example. And now people are thinking of ALD, expensive atomic layer deposition. This one is you could play with the precursor material, right? So yeah, that's the way that people do the doping. Mhm.
All right. Professor Kim, would you like to share your views on photoelectrochemical type optoelectronic synapses and other neuromorphic devices? And is there a possibility that they can be automated?
Oh, yes. So this is this oxide semiconductor now is already commercialized for display. So, it's very difficult for researchers, university and research center oxide semiconductor for display. No, they already manufactured more than 10 years. What about memory? Memory is very serious. They're not manufactured, but they're actively working on it. But relatively new area is this one. Okay, chemistry, photosensor. This is very new. And I mean, there are many papers that are coming out nowadays. So I think this scope is new. And one more time, this new material has wide band gap. Wide band gap has, advantage and disadvantage. Like, I noticed recently, this like phone makers, tablet maker, they are interested in NIR, infrared, infrared NIR sensor. Or some people try to, you know, block the NIR. The NIR is a good example when you do the, face recognition, right? They use NIR. So this area is relatively new. I think there are many things to do the research on this area. Yeah.
Thank you, Professor Kim. There's another curious question coming in from the audience. They would like to know, is there a possibility to use graphene that could work similar to indium gallium zinc oxide?
That's a good question. Graphene, when did it came out? Graphene, I think 2010, I forget, Andrew Geim and the other guy got a Nobel Prize, right? 2010, that was like, and I know there are many people working on graphene 2D material, but as far as I know, one of the biggest drawback, you know, of 2D material, including graphene, is the wafer level growing is, I was told, is very tough. So I know graphene could be not only for semiconductor, people use a transparent conducting metal, right? So many applications that I've seen companies for the using graphene, but I don't think the companies, display or memory companies are interested in 2D yet. Long ways to go. Yeah.
All right. There's another question coming in related to mobility. So for high mobility properties, are low temperature oxides which are produced below 100 degrees centigrade are relevant?
Ah, high mobility oxide is really new one. So there are many things, but reducing the processing temperature is very clear. People try to use like, flexible substrate or maybe minimize the manufacturing cost, right? But it's a little less relevant, the lowering the temperature to the high mobility oxide, I think. But I mean, the high mobility oxide is a new one, so I don't know. Maybe someone come up with a high mobility oxide with very low temperature processing. Yeah, it's a good topic too. Yeah.
Okay, moving to the next question. Could you please comment on some of the materials that could be utilized for memory and bioelectronic devices, or what are some of the selection criteria that makes a material better fit for memory and bioelectronic devices?
Uh, memory is easy. Memory, they have a clear, specification needed, like, high mobility or low current, reliability. But bioelectronics is tough. Bioelectronics, sometimes people ask gradable and biostable, in vivo, and this kind of experiment is this, metal oxide is not proven yet. Indium, indium is very expensive material, rare earth material, and is for the bio application, especially in vivo or inside the body, no, not yet. So this is new area. haven't seen actually biosensor or bio detector using this. This is blue ocean too. Yeah.
Okay. And would you like to comment like what are the main trade-offs between using crystalline materials and conductive polymer channels on such devices?
A good question. Conductive polymer material. Yes, I love to use conductive polymer. I mean, I was in company Samsung for 10 years. I'm now in the university 20 years. So that was a long time ago, right? I'm very much interested in polymer, but this especially the silicon-based conventional semiconductor manufacturing, transistor manufacturing non-succeeding, especially this organic material. So it's tough. So real as far as the reliability is concerned, but conducting polymer, I think is a good challenge, not for the semiconductor though, but other area, for other layers. You need the, material like conducting polymer. But so far, it's not very stable and not very reliable. Some reasons. Yeah. Okay.
Right. Quite interesting to know about that. Uh, Coming to the topic of oxygen vacancies,
Uh-huh.
would you please like to comment how do different oxygen vacancies affect the carrier concentration and stability?
Yeah, this is the hot topic. I did remember the slide that I showed you. They spotted, of course, it's incomplete bad material, amorphous IGs at all, it's oxide semiconductor. Because it's amorphous, it has many defects. One of the defects is oxygen vacancy. But oxygen vacancy itself is the electron. What a coincidence. So this is double side. You need to have oxygen bacon because it's an n-type semiconductor electron. But if you have too much oxygen bacon, too many oxygen vacancy, it acts as a defect. It acts as mobility limitation or reliability issue. So, uh, but think about one more time. People are commercializing this for more than 12 years, so they know how to do it. They're happy with it right now. Your phone, your MOLED TV, they're using it. So it's stabilized now, stable now. But if moving forward, like high mobility oxide, even next level, they are not ready yet. So, but more, I didn't show you here, but oxygen vacancy is still very important. But the next level is hydrogen. Hydrogen is the biggest headache for like Samsung display, LG display, and Samsung electronics. Hydrogen, hydrogen is the smallest one. It can go every places, right? It acts as a carrier sometimes, and sometimes it's just passivated and it depassivated, so it's not reliable. So this is a big issue. And I didn't present it today. So oxygen vacancy and hydrogen is very important issue. Yeah.
All right. One of our attendees would also like to know for semiconductor chip synthesis, are there any alternatives to the photolithography based etching methods?
Yeah, I mean there are nano imprint litho. There are some, but it comes down, especially like semiconductor is doing what? They are scaling down. They are making everything in nano scale, 1 nano, 2 nano, right? So people realize, oh, it's impossible. Photolithography and etching is the one for the manufacturing. Of course, researching, many, many other ways to do it. But so if you ask me in the future, maybe 30, maybe still photolithography and etching. And especially nowadays, semiconductor EUV, extreme UV. This is the hot issue and hot equipment. Yep.
All right. Coming back to another important topic that you discussed today regarding subgap states.
Yep.
So, at what defect density do the subgap states begin to dominate transport behavior?
Yeah, the subgap state is I forgot the typical value of a state, but now people. come up with a good modeling and good measurement way to actually measuring the, subgap state, NIT. So now the research is on, yeah, the hot topic is what's the change, how much the subgap state is changing after you do this. That's the big issue. And controlling the, the for the real actual device, they try to, maintain whatever the subgap state, because if the subgap is changing, it is affecting the reliability of the transistor. So yeah, that's the what's the engineering is going on there.
Okay. And a related question to that, are there any processing parameters that strongly influence the subgap state density?
Oh yeah, there are many. There are many, I think, uh, I mean, indium gallium is multi-component matter, right? It's the ratio and deposition temperature, the gas ratio, many things. Yeah. And yeah, after you do the process temperature, yeah, it affect a lot in the, you know, before and after the layer. Yes.
Okay. Uh, Good to know that. Another interesting piece of question coming in is, Professor Kim, do you envision a single oxide semiconductor platform supporting display, memory, sensing, and neuromorphic functions simultaneously? Or will application-specific material optimization will always be necessary?
Oh, that's a good question. High level question. Yeah. Yeah, I don't think there exists one universal oxide semiconductor. For each application, the requirement is different. So even the material itself is, that's the another advantage of oxide semiconductor. They can manipulate, they can easily play with the material and the composition. So yeah, I think it should be different. And I think different material, different phase. Yeah.
Okay. Uh, Moving to one more question. Given that many of these functionalities rely on defect states, how do you reconcile the traditional semiconductor goal of minimizing defects with the emerging paradigm of deliberately engineering them for functionality?
Could you one more time? Yeah.
Sure.
Yeah, I have to catch.
Uh, yeah, I will repeat the question. So, given that
Uh-huh.
many of the functionalities actually rely on the defect states, how would you reconcile the traditional semiconductor goal of minimizing defects with the emerging paradigm of deliberately engineering them for functionality?
Wow, that's a good high level question too. Yes, that's a good question. Yeah, oxide semiconductor, look at this amorphous phase. Compared with the single crystal silicon wafer, a huge defect. So I don't think they can replace the silicon. I don't think the defect like subgap states and all this dangling bond, you cannot really control. So some of the application, something like, you need a transistor, but most of time this transistor is off state. So which character is important? Off state characteristic or on state? Of course, off state. So oxide semiconductor is the huge advantage on there. So on this kind of a application, they use it, and I still think the silicon, you cannot you cannot you compete 100% with the silicon. So some applications, yes, yeah, yeah.
All right. I think with that, we are closing it towards the end of Q&A session. Again, thank you so much, Professor Kim, for your time and for that great talk.
Oh,
So would you
thank
like
you
to
so
share
much.
any
Yeah.
final remarks for our audience today?
I mean, I can feel, I've seen so many audiences. I really appreciate. I can feel your reaction in here, Seoul Yonsei University. So thank you so much inviting me and have a wonderful time with you. Thank you.
Thank you.
Thank you
Over